Hello, everyone. Welcome back. I hope you all had a great lunch, and let's continue the second part of Professor Xiaodong's talk. Welcome.
Okay, well, thank you guys for coming back from lunch. It seems like many people lost their way. So, but congratulations, you're finding your way back. And now, in the second part, I'm going to talk about mainly focus on the transport part of this FQH effect. So let me just introduce you the basic device structures. So personally, my background is not on transport. So whenever my collaborator propose these transport projects on TMDs, I always say, okay, I will let Corey Dean do it. If you know Corey, right, he's the expert in transport. So actually, I've been talking to Corey of the same project for many years. He always say he's going to do it, but he never did it. So at the end, I said, okay, well, we'll do it ourselves. The challenge, the reason we don't do transport because it's difficult to make a good electrical contacts with this TMD device. So the idea we're using is that, this is a cartoon of the device. This reddish is the twisted TMDs. Then we have a top gate and a bottom gate, and these black, attached to these TMD twisted MOT2 is electrodes. So what we do is for each electrode contact, we pattern a gate on top of it. So you can think of the local gate. Then once we turn on these local gate for each electrode contact, then we can get a reasonable contact resistance. So initially what we have is on the order of 100 to 200 kilo ohm. And now we can achieve each electrode contact on the order between 20 to 40 kilo ohms. So on the bottom is just the side image, right? We have these graphite gates. We have a local PT contact. And then on top, we have these local gate for each contact. Now the right-hand side is just optical image of a device with a 3.7 degrees. And the bottom is the atomic force microscopy image. So one thing you will notice, right, for these device, actually it's quite clean. So we don't have any bubbles or wrinkles on top of the surface. So for each device, what we do is we have this AFM tip just to squeeze out the bubbles. So my student tell me, right, each device actually takes about 200 hours. If he's lucky. It could fail at the 199 last step, right? Okay. Then this is the transport data we have for one of the device. On the left-hand side is the measurement of this longitudinal resistance, RxX. And vertical axis is electric field, horizontal axis carrier densities. And the right-hand side is corresponding measurements of a Hall resistance with RxY. Again, right, the vertical axis, electric field, horizontal is doping. It's always Hall doping. Now, you can see there's a lot of features in these data, right? So let's focus on these longitudinal resistance first. At the filling factor -1, and then near the zero electric field, you see there's a big red phase space with bluish color here. The blue color represents vanishing RxX, and the red means a very large RxX on the order of several hundred kilo ohms. And the black color here, what it represents is on the order of a mega ohm or even bigger, which is it's hard to measure in the low temperature. So you can see the vanishing RxX at the filling factor -1 associated with a large RxY. In this case, actually is quantized at a 1 HV square. So this phase space corresponds to the quantum anomalous Hall state. And the other thing you'll notice that if we apply vertical electric fields in these directions, right, there's a change of color, right, from blue to the dark means the resistance from nearly vanishing to very large number, only a few, only other megohms. So this shows that there's electric field induced phase transitions from the quantum anomalous Hall state to a charge-ordered insulating state. In this case, it's more like a mod state, as I talked to you in the first lectures. So there's a second phase space I would like you to pay attention is the filling factor -2/3. And again, right near zero electric field, you have the pocket with suppressed RxX. And correspondingly, we have these RxY, which is quantized at the 3/2 of HV squares. So these phase space correspond to these fraction chain insulator state. And again, right, if we go to a large electric field, these RxX will increase, correspond to these electric field induced phase transitions from these FCI state to a charge order state. So between the filling factor -2 and the -1 to -2/3, you see there's a pocket of a suppressed RxX. Yeah. And correspondingly, right, you will see RxY also suppressed, but it's not vanishing. In this color scale, because we are in a unit of quantizations, right? That's why RxY looks like almost vanished, but actually it's about a couple kiloohms. And the RxY is a smaller than RxY, but non-vanishing. So this phase space, we call it a fractional. We call it a ferromagnetic metal phase or anomalous Hall metal phase. Then lastly, there's another phase space associated with 1/2 here. And correspondingly, right, you see there's a finite RxX also associated with very large RxY. And these are the phase space we assign to these putative composite liquid phase. So there's one more little feature I want you to pay attention, and I hope somebody can help us to understand is that if you think about, focus on this filling factor about roughly about 0.9, you will see that the RxX, right, at the 0 electric field, RxX is suppressed, but the finite, right, it's not 0, it's suppressed, and also RxY vanish. However, if I increase the electric field just near the phase transition boundary, you can see there's a revival of this quantum anomalous Hall state, right? RxX actually vanish with RxY coming back near quantized. So we're not exactly sure what the state is. It could be some kind of a quantum anomalous Hall state, but with some charge orders. It's just a speculation, but I think this is actually kind of interesting because by application of a vertical electric field near phase transition boundary, there's a revival of these quantum anomalous Hall state. Okay. So now let's look into details. And first, let's focus on the filling factor -1. What I show you here is a measurement of RxY by sweeping the magnetic field forward and backwards. Right at the bottom, you will see that RxY actually is quantized at the 1 HV square at the 0 magnetic field, and correspondingly, RxX is strongly suppressed. So this is the hallmark of a quantum anomalous Hall state. And one nice thing about the twisted TMD is that the phenomena is highly repeatable. So as I talked to you at the beginning, right, if you think about graphing system or other system, realize these quantum anomalous Hall state. What I mean, other system is 2D materials. It's actually, it's hard to, the quantized Hall effect is not easy to be repeated. But this is not the case for twisted TMDs. So far, we already have maybe 15 to 20 samples shows a very robust quantized Hall effect. And the other, I think one of the reasons is that the quantized Hall effect or this quantum anomalous Hall effect in the twisted MOT2 it's not as doesn't sensitively depend on the twist angles. Okay, so far, right, from the results from the whole community, we know that these quantum anomalous Hall effect exist from twist angle around 2.1 degree all the way to 4.2 degrees. So you can see there's a large twist angle for these QH effect. Here, what I show you is the 4 device from twist angle 3.5 degrees, 3.7, 3.9, and 4.2. You can see that they more or less look similar, right? We have these quantized RxY at the 0 magnetic field with a suppressed RxX. So now we're going to look at these fractional fillings. So let's look at the -2/3 fillings. Right here, I show you the bottom is the measurement of RxY by cycling the magnetic field, and the top is associated RxX. So you can see that RxY is quantized, right, at the 3/2 of HG square with suppressed RxX at 0 magnetic field. So that's just consistent with this FCI state. And we can do the same measurement for the filling factor -3/5 Again, right, at the zero magnetic field, we see nearly quantized RxY, and we suppress RxX. So that's also supports we have these FCI state at also 3/5 feelings. So one of the important feature of the system is that the energy gap of these FCI states is really large. So what I show you here, the measurement of RxX and also RxY as function temperature, right? From the top, it's 100 millikelvin, all the way to the bottom is 3 kelvins. So what I would like to emphasize is that even at the 2 Kelvin, you'll see these RxY is still nearly quantized, and we suppressed RxX. So this really suggests that the system has a very large energy gap. So this the data from these minus 2/3 feelings. So I didn't show you the data, but for the quantum anomalous solid state at the integer feeling, right? It nearly quantized between 6 to 8 Kelvin, so it's very high energy scales. So far, so I think I talked to you, right? We have these FQH effect, but there's some immediate question I'd like to address, right? The first one is, can we see the bulk edge correspondence of these intrinsic property of CI? So what it means is that, right, when we say there's FCI states, it basically means the bulk is supposed to be insulating, and there's conducting edge states. But from all these transport measurements, we don't really see that. What we have is we infer this property, right, from these quantization measurements. So it would be ideal to directly show these bulk and edge correspondence, right? To probe the bulk, show it's insulating, and then measure the edge, show it's conducting. The second effect, as everyone knows, if you're working on moirés, right, and you just want to know what is moiré disorder effect, how it impacts these measurements. Then I'll really show you, right, when you apply electric field, we can introduce certain phase transitions, right, from these either QH or FQH to these charge order, the insulating state. So I want to know a bit more about these, the nature of these phase transitions. And then the next question is, what's the thermodynamic gap of the systems? So from the transport measurements, I show you that the quantization can survive to high temperature, right? So for example, like 2/3, I show you that it survive to 2 kelvins. For -1 QH state can survive to about 7 to 8 kelvins. But we know that when you increase the temperature, right, because the gap I talked to here is the correlation induced gap. So it basically changes function temperature, right? So I want to know what is really the gap, for example, at the base temperature, okay? So to address all these questions, we collaborated with a couple groups. So the results I show you first is from the collaboration with Andrea Young's group at Santa Barbara. So in these measurements, what Andrea did is they used these Nano-SQUID, right? Nano-SQUID is a tool you can imaging the stray field on the material systems. So just illustrate that these schematic here, right? They have this tip with a spatial resolution on the order of 200 nanometers. Then they map out the stray magnetic field across the samples. So on the right-hand side, what I show you is the measurement of a static magnetic field as function of an electric field, and also as function filling factor in this horizontal axis. So you can clearly see that, right? In these phase space, these hole dopings, and with a certain electric field, you have this non-vanishing, right? They measure these DC magnetic field, okay, on the order of micro Teslas. So if I compare these measurement with my magnetic circuit diagram and determine the phase diagram, you can see these two actually looks almost identical, right? Again, these in the middle, right, bottom panel I show you here is the circuit diagram measurement, as I talked to you during the first lecture. And on the right-hand side is Nano-SQUID measurements, right, from basically on a spot inside the samples. So both show you the same magnetic phase diagrams. So this shows that the system, as I talked to you, right, it's kind of robust. And then what we can learn from these Nano-SQUID measurements is that we can measure the DC magnetic field as function filling factor at a fixed electric field. So here, this is what the red curve is showing here, right? Okay. Then what Andrea can do is that he can also do these AC measurements. Basically, they can either measure for example, they can modulate the electric field, or can modulate the carrier densities. They can measure the change of the DC magnetic field. Okay, it's an AC measurement. A simple way to think about it is you can think of it as the blue curve they got here is from AC measurements, which is a derivative of this red curve. Okay, the nice thing about these AC measurements is that you get higher resolutions. Then you see multiple states appear, right? For example, at the filling factor -1, you see a state. They also see multiple fractional state, -2/3, -3/5, -4/7, and -5/9, for example. So there's multiple states appeared in these measurements. So one nice thing we can learn from these measurements is to extract the thermodynamic gap, right? To walk you through just simply how we understand these associate, when you have these chiral edge states or topological systems, these edge states actually also contribute to these magnetizations. The contribution is described by these formula here. Delta M means the change of magnetizations by tuning the chemical potential across these chains of the gap. And the C is the chain number. Delta is the gap, and the phi now just a flux quantum. Okay, so basically from this equation, what you can do is, from these measurements, for example, right, at the -1, you see that when tune the chemical potential of the doping, right, across these chains later, you see these DC magnetic field actually drops, right? There's a sharp drop. The reason of this sharp drop because these total magnetization coming from the chiral edge states also reduces. The reason it's drop because the chain number C is negative, it's a -1. So you can imagine if we switch the chain number to positive, then these will go up, okay? So then from these measurements, Andrea can infer the change of magnetization when the chemical potential across the gap. And from there, he infers these thermodynamic gap of the systems. So when I say thermodynamic gap, means a gap of single particles. It's not a fractional charge gap. So from these measurements, he inferred the thermodynamic gap is 14 average, right? It's 14 millieV for these -1 state or quantum non-solid state. And for the -2/3 state, he shows that the thermodynamic gap is on the order of 7 millielectron volt. Of course, right, you see there's many curves here, means these curves are coming from different parts of samples. Shows that the sample is actually, this particular sample we sent to them has a moiré disorder in the systems. So let me just comment a little bit on this number, right? 7 millielectron volt, which is thermodynamic gap. As I showed you, it's a single particle gap. We also did the thermal activation measurements of the 2/3 states. What we got is that the gap is about a 2 millielectron volt. Okay, so it's about 3 times smaller than the thermodynamic gap, which actually makes sense because in a transporter, what you measure is a quasi-particle. It's a fractional charge gap. In this case, it's 1/3, right? But the single particle gap is supposed to be 3 times larger than that. So I think everything kind of makes sense here. So then now I'm gonna talk about another local probe measurements from my collaborator, right, Xiaodong at the Stanford, and with postdoc Judy, Mark. So in these particular measurements, the aim is to probe these bulk edge correspondence. And within ZX group, they develop these microwave impedance microscopy. Okay, so basically, in a nutshell, you have local probe to measure the conductivity of the samples. So for these local probe measurement conductivity, there's an open challenge is that it's hard to put a top gate on a sample, right? Once you have a top gate, imagine you have a tip try to penetrate through the top gate and measure the conductivity at the bottom. The gate usually will screen out the tip. So it's difficult to measure what's going on underneath the top gate. And the trick, what we use here is that we have a monolayer WS2 on top as a top gate. So monolayer WS2 is another transition metal dichalcogenides and the semiconductor. So it's actually it's an insulator, right? But the trick is in ZS group, they develop these light-coupled beam measurements. So once you shine light to these mono WSC2, you actually inject photo carriers. What's magic here is that these photo carriers, they are mobile enough to enable the mono WSC2 as a good gate. But at the same time, this carrier is not mobile enough to screen out the tip, okay? So basically from these light-coupled mono WS2, then where lies these top-gated sample, then we can measure what's the local conductivity inside the sample. So on the right-hand side, what I show you is the measurement of these MIM signals as function of a electric field in this vertical axis, and the horizontal is carrier doping. In this color plot, right, the dark color means it's insulating, and the bright means the sample is conducting. So you can see that in this plot, right, clearly near zero electric field, you have these insulating phase at the filling factor -1, -2/3, -3/5. So this is right. These are basically consistent with what the phase diagram I show in the transport, because at these three states, they are fractional translated state. What it means is the bulk is insulating, and only edge is conducting. So what these mean measurements is exactly they measure the bulk conductivities. So what they show is that whenever there's a FCI states, bulk is insulating. So second, what you can pay attention is so let's just focus on this, right? Let's take a line cuts first near zero electric field. So these line cuts, you will see the blue curve here is at the 500 millikelvin, the red is 1.5 Kelvin. Let's just focus on the blue curve here, right? You see the filling factor -1. There's a suppression of local conductivities, and same happens at the filling factor -2/3, -3/5, and the -4/7. So these measurements basically tell us that right, it's another way to probe these fractional changeless state. Okay, it's a local conductivity measurement. Next, we can take a line cuts by fixed doping, but tuning this electric field along this line. So just by looking at the color, right, you can already tell that by changing electric field, the color changes from dark to bright to dark. This means there's a transition from an insulator to a metal to an insulator. So here I take line cuts at the two fillings. The blue is at the filling factor -1, which is the quantum anomaly state. And the green curve is from at the filling factor -2/3. This corresponds to these FCI states. Now you will see that at the low electric field, the system is in these right in this chain insulated state, means the bulk is insulating. So you can see this local conductivity actually it's suppressed, right, as the measurement shows. Then near the phase transition boundaries, the conductivity actually rises. This means the system now at the phase transition boundary, the gap actually closes, and the system becomes metallic. Then as we keep increasing the electric field, the system transition into another charge ordered insulating state, evidenced by these suppression of local conductivities. So if I compare these local conductivity measurement with these transport measurements, you can see the phase diagram looks basically identical to each other, right? We have these quantum anomaly, fractional quantum anomaly with putative FCI state, etc. And then we have the electric field induced phase transitions, and everything looks the same. But I want to emphasize, right, these two are very distinct measurement technique. One is from electron transport, more like a bulk measurements, and the other is the local conductivity measurements by a microwave impedance microscopy, but they tell you the same phase space. So another nice thing about these local conductivity measurements is they can do spatial mappings. So what I show you here is the MIM signal, right, as function of space in the XY axis. So on the bottom right corner, I show you the optical microscope image of samples, or FM image of samples. And these black square highlights where, right, this MIM scan happens. So if we focus on the filling factor -1.33, the system actually into metallic regimes. So that's why you see that these MIM signal actually, right, lights up in whole samples here, okay? And on top, that's the substrate outside the samples, which is dark. So now we start to tune the filling factor, right, from this metallic region all the way to filling factor near -1 is in the quantum anomalous solid state. Now you see that inside the bulk, it's dark, means that now it's insulating. But the physical edge here, right, it's bright. So this shows that we do have this quantum anomalous state, which is insulating in the bulk, but conducting on the edge of the samples. Then we can continue tune the filling factor. Eventually, for example, at the -0.78, which is the ferromagnetic metal phase, you see the whole sample, right, lights up again, become a metal. So the measurement can continue to the fractional filling regions. For example, near the fractional filling at the -2/3, you see bulk is quite insulating with conducting physical edge. And also happens at the -3/5 filling. The contrast at -3/5 filling between the bulk and the edge is not as evident as the -2/3, right? That's because the gap of -3/5 filling is not as large as the -2/3 state. And one more thing what we can learn is because it's local probe. So you can probe different parts of samples and look for domain effects. So what I show you here from the top curve is coming from region 1, which is highlights here, these blue dots. And the reddish curve is coming from region 2, which is this orange curve. So in these two plots, what it shows that at least a fixed gate voltage, actually for region 1, we're already in the state with -3/5 fillings, right? All these -3/5 FCI state. But for the region 2, it's a -2/3 FCI state. So this measurement shows that it's possible, right, to engineer a domain boundaries between two fractional orders. Right? These two orders have different chain numbers. They share these domains. So I think it's possible. That means we can really carefully design our samples and to create these topological domains with different fractional orders. There's some interesting physics we can do there. Okay, so far everything I talked to you, right, as you heard, is that all the state I talked to you follow the gene sequence of a fractional quantum Hall state. Okay, right? And also this is the experiment, but also there's a lot of theory has been done in the field, and all the theory points out that also this, right, suggesting the filling factor larger than -1/3, right, is everything in the first chain band shares features with those of lowest lambda levels. Okay. And then the question I want to ask is, can we go beyond this? Right, we know that, for example, right, in the n equal to 1 lambda levels, there's these famous 5-half states, which is promising candidate for non-abelian states. Then it's possible to create a flat chain band, which can mimic the n equal to 1 lambda levels. Then we may have a chance to look for these even denominator FCI states, then with possibility of non-abelian aliens. So here I highlight just a few theory papers, discuss the possibility of these, how can we create the flat chain band to mimic the n equal to 1 lambda levels and the possibility for non-abelian aliens in the twisted MOT2. So all these just kind of motivation for us to study the chain band with higher energies, right, of the second chain band. So let me just remind you again. What I highlight here is these magnetic circuit diacrisis measurements, right? And when you see that there's non-vanishing MCD signal, basically means we have these ferromagnetic orders, right? Now what I'm going to do is I'm going to extend these measurements to higher filling factors. So these MCD measurements, right, what I highlight this part to the filling factor -1, basically it's the same as I showed you. But then we extended all the measurement with measurement to filling factor -3s. So you can see that the MC signal actually vanishes for filling factor -2, but it appears again near a large phase space of filling factor -3s. So this suggests that at the filling factor -3, basically we're already doped to the second moiré band. Okay, so this suggests that the second moiré band also has these strong cooling interactions or direct cooling exchange and give rise to these ferromagnetism in the systems. So we can study a bit more of ferromagnetisms. And the first, right, let me just go back to minus 2/3 feelings, right? You see these hysteresis loop of MCD as function feeling magnetic field. You can do the same thing for the -1, and you can see something here. Then we can go further, right? If I measure the -2 feelings, there's absence of a hysteresis curve. So it shows that the -2 actually doesn't have ferromagnetism. But when you go to -3 with a beautiful hysteresis loop, it shows that indeed, right, these feeling factor -3, we have a ferromagnetisms. So we can compare the Curie temperature for this particular sample at the trace angle 2.6 degrees, right? We measure we measure this MCD signal as function temperature. We increase from 2 Kelvin at the bottom all the way to 9 Kelvin at the top. So this just suggests that the Curie temperature for feeling factor -1 is about 9 to 10 Kelvin for this 2.6 degree sample. Then we can look at the same measurements for the feeling factor -3. Right, from bottom to the top, I increase temperature from 2 Kelvin to 6 Kelvins. So this shows that the Curie temperature for the -3 is about 6 Kelvin. So all the information I give it to you here shows that the ferromagnetism at the feeling factor -3, or the other way to think about it is when you feel the second moiré band, actually it's quite robust. Okay, so this just take-home message, right? We do have ferromagnetism at the feeling factor -3 when you feel the second moiré band. And next, we'll look at these transport measurements, right? I want to see how it look like. So now we perform the transport measurements of this trace angle at the 2.6 degrees. The data I show you here, right, it's already symmetrized or anti-symmetrized at 100 millitesla. So on the left-hand side, right, at this point, I hope you're already familiar with this, right? Data is that it's a measurement of Rxx. In the vertical axis, electric field. Horizontal is my feeling factor. And the right-hand side is corresponding Rxy. So in this particular plot, right, there's a few features on the highlights, right? At the feeling factor -1, you see there's a vanishing Rxx, which is the quantum anomalous Hall state. And the -2/3 feeling, there's a pocket that suppresses Rxx. That's the FCI state. And the feeling factor -2, there's some kind of a recessive states here. So that's in a theory, and also the reason there's some experimental reports suggest this could be a quantum spin Hall state. But then all you pay attention is that the feeling factor -3 here, okay? There's a suppressed Rxx. Now we look at the Rxy, right? On Rxy side, we have a feeling factor -1. We have larger Rxy. It's a quantum anomalous Hall. At the -2/3, we also have an even larger Rxy. That's the FCI. And the feeling factor -2, there's a vanishing Rxy. But at the feeling factor -3, we see enhanced Rxy, correspond to this suppression of Rxx. But the Rxy is not quantized in this case. So it means that it's not a quantized anomalous Hall state. But suggesting it could be. So I can show you a bit more evidence. So the other feature I want you to pay attention is the sign of the Hall signal at the feeling factor -3, right? So you want to look at the feeling factor -1 and the feeling factor -3. You will see the color is the same, right? It just, let's don't talk about plus or minus, but look at the color, they are the same color. It means the chain number for the state at the feeling factor -1 has the same sign of the chain number at the feeling factor -3. You can think of the chain band for the first band and also second band, they have the same signs. But the trace angle I highlight here is a 2.6 degrees. Okay, so we can look at the data a bit more carefully. So again, here I show you just the line cuts from the data I showed previously. Then we measure that as function temperature. Right? On the left, hand side show you from the RxX, and from right-hand side is a measurement of RxY. Now, again, right, at the -1, right, you see these quantized normal solid state with RxS go to 0. And for this particular sample, -2/3 state, these RxX are quite large here, but you can see clearly a dip. But what you pay attention is that the corresponding at the filling factor -3, when we cool down, right, from 12 Kelvin to 50 millikelvin, now you can see there's a dip actually forms here, right? Then you can look at the corresponding RxY. As I cool down, right, the RxY actually quickly rises to a large number. And on the slightly larger than these RxY is slightly larger than RxX. This also suggests that we have these incipient chain insular state. And again, pay attention to the sign of these RxY, right? At the filling factor -3, they have the same sign of the chain number at the -1. Sorry, the RxY has the same sign, so it means the chain number has the same sign. Now, let's look at the different sample at a complete different twist angle at a 3.8 degrees. Let me just remind you, right? Previously, what I show you the data is from 2.6 degrees. Now the data is coming from 3.8 degrees. So what I show you here is these residual RxY, or called delta RxY. Means only the hysteretic component of my RxY, okay? Now by looking at this data, you see there's a very large anomalous Hall signal at the filling factor -1, right? That's just my quantum anomalous Hall state. And at the filling factor -3, we have a finite RxY, same as 2.6 degree, but there's one thing different. The difference is now you see the sign of my anomalous Hall signal, RxY, at the filling factor -3 is opposite to the sign of the filling factor -1, okay? So this just tells us that at the 3.8 degrees, the chain number of the second band has opposite signs of chain number of the first band. And to just understand this a little better, what I show you here at the top, right, is these the hysteretic curve of these RxY at the filling factor -1. So you can see, right, goes in this way. But look at the bottom, which is the same measurement, but at the filling factor -3. Now you can see the hysteretic curve is actually has opposite to the top, right? The top, if you go from the lower field to high field, the RxY is actually from positive to negative, but it's exactly opposite for filling factor 3. When we increase the field, the RxY actually from negative number to positive number. Okay, so this just tells us we do have opposite sign of chain numbers for the first band and the second band at the filling factor at the twist angle 3.8 degrees. So to just for comparison, right, to convince you, now I plot these data, RxY and RxX for 2.6 degree and 3.8 degree together. The key message, right? Let's focus on the sign of the Hall signal. For 2.6 degrees, at the filling factor -1 and the -3, RxY has the same sign. But you look at the 3.8 degrees, the filling factor -1 and the -3, the RxY has the exact opposite signs. Okay. So we can further confirm the system is right at the filling factor -3 is a chain insulator, and also confirm the sign of the chain number. We measure these RxY and RxX as function of a magnetic field. So these data, what I show here, the top is RxX, the bottom is RxY. You can think of Venn diagrams. This y-axis is magnetic field, and all the way to about 13 Tesla. So with these data, right, you can see that we have these quantum anomalous Hall state here. We have this FCI state, and you see there's a suppressed RxX, and with a finite RxY here. So importantly, if I just draw these linear diagrams, what I have is the slope of this quantum anomalous Hall state is -1, but for these chain number, for the filling factor -3, right, the slope actually is +1. So let's just tell you, indeed, the chain number of the filling factor -3, this has opposite signs of this quantum anomalous Hall state at the filling factor -1. So at the bottom, what I show you is just line cuts of the data at the 8 Tesla. So what I want you pay attention is that you look at these RxY. First of all, has opposite signs at the filling factor -1. Second, it is quantized to HV squares. Okay, it suppressed RxX. So it is a chain translator. Then we can do the same analysis or same measurement for the filling factor for the twist angle 2.6 degrees. Again, there's a lot of interesting features in this plot, but I want to emphasize is let's focus on this data filling factor -3. Now you see that the slope actually is negative, and it has the same sign with the filling factor -1. Okay, so both has chain number -1. Right? And there's many other features I'm going to talk to you in details, but that's just we know that the sign of the chain numbers, they're the same signs. So the measurement back here actually is consistent with the prediction from my colleague Dichal, right? He's going to give the second lecture this afternoon. He will tell you more about details. So what's happening, what I show you here is the highlights of the calculations, right? From 2.45 degree and a comparison to 3.89 degrees. So these 2.45 degrees, you look at the first chain bands, both of them has the same sign, which is -1, but at 3.89 degrees. The first band and the second band, they have opposite signs, -1, +1. So they're going to tell you, right, why the sign of a chain number will change as function of twist angle. But in a nutshell, what happened is, from the experimental point of view, right, what you have is in these twisted TMD systems, there's a two polarization coming into play. The first one is that there's a charge transfer from one layer to the other layer. So this gives you a dipole in the vertical directions. So this contributes to the moiré potentials. At the same time, in the system, there's a strong lattice relaxations. So this lattice relaxation gives you an in-plane strain gradient. That gives you a piezoelectric polarizations. Then that also contributes to the moiré potentials. So then these in-plane piezoelectric polarization will compete with these out-plane electric dipoles. And this competition, it depends on the twist angles. So the large twist angle, for example, right, the charge transfer dominates, will give you one sign of chain numbers. And we go to small twist angle, the in-plane, these piezoelectric polarization actually dominates because lattice relaxation become stronger at the small twist angles. So that gives you different signs. Okay. Now, I want to provide you further evidence is our understanding is correct, right? The assignment of the chain number. Again, remind you, right? The chain number at the 2.45 or small twist angle for the first and second band is -1, -1. Now, what I'm going to show you here is that let's look at these phase near filling factor -2, especially at this corner here, right? At the large magnetic field. You'll see that Rx is suppressed with very large Rxy. If I take line cuts, what you see here, Rxx actually goes to 0, and with Rxy quantized with chain number 2, actually -2 here. So this shows that at the large magnetic field, we actually have these chains formed, right here. So why there's the formation of chains like the filling factor, with the chain number -2? To understand this, we can think about how the band evolved. And for example, at the B equal to 0, right, at the 0 magnetic field, I show you there's two values, two copies. One is +k, there's a -k. So these two copy values, they have opposite spins and they also have opposite chain numbers. Right. Let's look at the k values. The top of valence band with chain number -1. Then in the -k value, the top of valence band with chain number -1. Okay. So the total chain number is 0. So when the filling factor -2 means that both top valence bands are occupied, and the Fermi level is in a gap. In this case, right, the chain number is a zeros. That's why we see a resistive state. And again, in this case, right, theory suggests this quantum spin Hall state with some experimental evidence to support these interpretations. But what you pay attention is that clearly when I increase my magnetic field, there's enhancement of RxX. Basically, there's a phase transition happens here, right? This might induce phase transition. So this phase transition happens is because when we apply magnetic field, there's a Zeeman shift between these opposite values. Okay, so one value for K is the band is moving up, the other one is moving down. Now you will see at the critical magnetic field, there's a band crossing between the second moiré band of the K value to the first moiré band of minus K values. Okay, so there's a band crossing happens, right? So once this band crossing happens, now when you tune the Fermi level, right, to the gap, the top two bands is coming from the same valley, and they have the same chain numbers. So you can just count it, right? The total chain number now is -2. That's why we have these chains that appears with quantization at the 2e square of h. Okay, so what I'm showing here, right? First, it supports that our assignment of a chain number for the first two bands the same sign. The second is I show is actually there's a magnetic field induced band crossing between these two valleys. It's a topological phase transitions and give us these change into the state. Now there's another feature I want to pay attention. Once this magnetic field induced phase transition happens, actually there's an incident state appears. This incident appear is at the filling factor actually -3/2. So we can really kind of visualize these states a bit more. Is I take these measurement of Rxx as function of electric field and the filling factor as magnetic field at 7 Tesla. So where the phase transition just happened. Now you can clearly see that there's a phase space with a large Rxx at the filling factor 3/2. So what's happening is that when the phase transition happens, right, my second moiré mini band just got isolated. Then once the second moiré mini band isolated, at the 3/2 means it's a half field of the second chain band. So my data shows that in the half field of second chain band, actually the system gives rise to this charge ordered insulin state. So I think hopefully this will give us some feedback to the community is because there's a reason you will hear from next talk is there's a possibility to engineer non-abelian alien states at the half field of second chain band. And I want to give feedback is we have to go look for different twist angles. At least 2.6 probably won't work. Okay, so this is another take-home message, right? Charge order state is favored of the even denominator FCI state at filling factor -3/2, but for the twist angle 2.6 degrees. So you probably heard of exciting progress on a twist angle about 2.1 degree, right? So last December or November, my colleague Dixiao and Ting Chao, right, told me that they found something exciting. So that's actually a paper you will see is submitted actually at the November 2023. So what they found is that there's a match angle for second chain band at the 2.1 degrees. So here's the highlights. What I show you here is average density states of the band. The blue dots represent from the first chain band. The orange is from the second chain band. And the horizontal axis is just trace angle. So we see that for the first chain band, right, there's a range of angle as really large dots, right, between, near 4 degrees all the way 2 degrees, so the dots is large. So there's no matching angle. But if you look at the dots for the second band, Actually, there's a singularity near 2 degrees. So there's a possibility of there's a magic angle, means the band is really flat. Now, the question is well, then there's a hope, right? We can see these exotic states at the fraction fillings or fillings of these second band at these near 2 degree samples. So when Dee told me these results, and I told my students, right? So they all working on these 2.1 degrees, but turns out that it's very challenging to make a good transport samples because the small trace angle lattice realization becomes significant, and it's very difficult to make a good sample with homogeneous moiré disorder, number one. And the second is that most time actually the sample just relaxed. So we don't get the good samples. So early this year, right, and the Cornell group actually reported these results from, they're able to actually make one device at the 2.1 degree and perform transport. I think it's a really exciting progress because we know that how hard it will make even one device at the 2.1 degrees. So the take-home message from this paper is that they show that there's evidence of fractional quantum spin Hall effect in these 2.1 degree samples. Okay, and then what I highlight here is one of the key observation of their measurements is there's a zero anomalous Hall connectivity at the filling factor -3. So then these results really excites the whole community. Especially there's a lot of theory proposed trying to understand what this state is behind these the evidence of fractional quantum spin Hall. So there's two camps. One proposed the state actually has time reversal symmetry. The other camp proposed the system actually time reversal symmetry actually already broken. So I took my students, right, before we can make a good transporter device, let's take a step back and just understand whether the system has a magnetism or not. At least we can help the theorists, right, to constrain. They won't go too wild, right? Constrain them into one half, either with the time reversal symmetry breaking or not. So here's the results we have. The measurements done by my postdoc Wei. So I'm gonna just show you the main results from these 2.1 degrees, okay? And again, hopefully at this point, right, you are familiar with these MCD measurements. So I'm not going into details again. You can clearly see, right, there's a non-vanishing MCD signal near the filling factor -3. And there are also MCD signal at filling factor -1. The data is taken at the zero magnetic field. So this data basically clearly shows that there is a ferromagnetic order, and actually in a large phase space of a filling factor -3s. So it's a robust. The data actually shows that there's a significant spin fluctuation with system as we tune the carrier densities. So we can suppress this spin fluctuation, just do the measurements again at the 50 millitesla. Now you can see the data actually much more smooth. But it doesn't change the conclusion. There's a ferromagnetism at the filling factor -3 for the twist angle 2.1 degree. To confirm that, we can perform these MCD measurements as function magnetic field. Right, on the right-hand side is the MCD at the filling factor -1, and the left-hand side is MCD at the filling factor -3. You see a beautiful hysteresis. So I think there's we have a pretty comfortable to say that we observe this ferromagnetism for this 2.1 degree of the second chain band. And again, right, we can explore the phase diagram a bit more. So what I do is we can just subtract this blue curve with respect to this red curve, okay? Take the difference of them. Basically, we got this hysteretic component. Then we plot it as function magnetic filling factor and magnetic field. Now you can clearly see where these ferromagnetic phase space, right? The ferromagnetic phase space actually, that's very interesting, at least for me, is that for large trace angle, the ferromagnetism actually stops at the filling factor between 1.2 and 1.3. But you look at this data, first of all, there's no FCI. Right? The ferromagnetism actually stops just a little bit below -1, but it extends all the way to beyond 1.5. So I think it's interesting. Means even though there's no FCI for the first band, but there might be something interesting at the 3 half fillings. We don't know yet, but it shows that there's ferromagnetism, at least the first ingredients, right? We have it. We have a spontaneous temporal symmetry breaking. The second is that also there's a large phase space of a ferromagnetism around here, near filling factor -3, which is second band. So we can bit more, right? Perform the temperature-dependent measurements. So on the left-hand side, the top, just the electric field dependence of this hysteretic component shows that we can also use, right? Just anything, everything is consistent. We can use electric field to control the ferromagnetism, and it shows that the signal can survive all the way to about 5 kelvins. Okay, this is for filling factor -1, but for filling factor -3, we can also use electric field to control the ferromagnetism, and again the Curie temperature about 3 Kelvin. Okay, so let me just comment the Curie temperature a little bit, right? If you remember, I show you that the Curie temperature for 3.74 degree sample is about 14 Kelvin for filling factor -1, and for 2.6 degrees, the Curie temperature about 9 to 10 Kelvins. Now for 2.1 degree, the filling factor, right, -1, the Curie temperature keep drops to 5 Kelvins. So everything I think is consistent because the magnetism coming from direct Coulomb change. So when you reduce the trace angle, means you enlarge the moiré size, right? Then the absolute carrier densities, or you can think of the separation between the carriers in moiré orbitals actually become larger and larger. Therefore, right, the exchange interaction will become smaller for smaller trace angles. That's the reason why the Curie temperature actually reduces as we reduce the trace angle. So everything is consistent. But the take-home message is we do have ferromagnetism at the filling factor -3 for the match angle 2.1 degrees. So I hope this will be useful, for the community to understand what's really going on for this state. Okay, so here I'm gonna summarize my talk, and I steal this beautiful phase diagram, actually in a review paper by Ali Astani and with Calvin. This phase diagram is our data, but we never thought that we could plot as pretty as Ali did. So I show these instead of my own data. I think it's much more clearer. So right in phase diagram, you will see that for the first chain band at the filling factor -1, right, you have this quantum anomalous Hall insulator. And by apply this electric field, you can go to this correlated insulator, which is, I believe, is a Mach state. Then at the filling factor -2/2 and the -3/2, -2/3 and the -3/5, right, we have this FCI state. But by application of electric field, again, there's a phase transition, right, to charge order state. And between the FCI and the QH state, there's a ferromagnetic metals. Then at the filling factor -1 near 0 electric field, there can be an anomalous composite film liquid or CFL state at 0 magnetic field. And the application of this electric field will drive it into some kind of a charge ordered state. Then below the filling factor of -1, what we see is all charge ordered insulin state, which is topological trivials. Then there's a second phase diagram. I think it's my student put together. So previously, right, it's for the first chain band, but the vertical axis is electric field, horizontal is filling factor. Now the first chain, this phase diagram, what I show you here, horizontal axis is filling factor, go whole doping, and the vertical axis actual twist angle, and this is a phase diagram at the 0 electric field. So from this phase diagram, what we're trying to show is that there's also twist angle is actually very powerful tuning knob, even though the state is kind of robust, right, within large phase space. And what I show you here is basically at the 3 half filling, for example, at the 4/3 filling, there's a possibility of exotic states such as FTIs or nonabelians. Recently, right, Andre, Nikolai, and the collaborators had some, I think, pretty exciting theory to explain the possibility of TI state at the 4/3 fillings. And the -2 filling, there's a recent experimental progress with a lot of theory shows that there can be a quantum spin Hall state. And there's also, right, a possibility at the -3. At the large trace angle, I already show you. Start with a incipient changeless state, and the chain number can change the sign from plus to minus as we tune twist angle, and eventually reach to this match angle 2.1 degree. There still could be exotic state. We just don't know yet. Okay, so in summary, I think this pretty exciting time actually to study these interacting topological physics, right, with a spontaneous time reversal symmetry, use these 2D materials or moiré systems. And you know that right here highlights right 1980s we have a quantum Hall effect, and then 1982 the fractional quantum Hall effect was discovered. About 30 years later, then this quantum Hall effect, but that zero magnetic field or quantum anomalous Hall effect was demonstrated in this magnetic doped topology insulator. Then last year we showed that we can realize this fractional version of a quantum anomalous Hall effect, or this latest analog of fractional quantum Hall at the zero magnetic field in twist MOT2. So I think it's a pretty exciting time. And I just want to compare the state of the art of a 2-deck system. Right here I show you, this is reproduced from this beautiful paper of a 2D electron gas from gallium arsenide. The measurement of RxX, you can see there's basically many beautiful fractional states, right, with these high mobility sample. The mobility probably on the order of 30 million to 40 millions. And this is our, I would say, pretty lossy data compared to previous one. Right, we measure RxX as function filling factor. We do have several states, 1, 2/3, 3/5, 4/7, 5/9, blah blah. But nowhere close to what you can do with 2-deck system, because the sample quality is not there yet. But however, I would argue that there's a lot of opportunity provided to us, right? Hopefully, I already show you today, is you have these unique twist angle controls, and for the twisted 2D materials, right, we have these simple knobs like doping, electric field we can control. In the lab, we also develop many other knobs, such as a strain, right? And we can use. Also, I show you that the system has large gaps, close to terahertz, right? So it's possible to use these powerful terahertz spectroscopy to control this many body gap. And I also show you today, there's a chance, right? We can use optically excited state on the order of 1 eV, actually to probe this many body ground state on the order of 1 to 10 millieVs. So I think it's another unique opportunity provided by this twisted MOT2 system. Last but not least, I think there's also provided opportunity to do photo emission spectroscopies, because we know that the photo emission spectroscopy, this photo emission electron doesn't like a magnetic field. And also there's limitation, right, on temperatures. So in the past, it's challenging to do photo emission spectroscopy of these fractional excitations. But I think twist MOT2 might just provide this opportunity to do that. So with that, I'm going to thank all my collaborators, right? I'm not going to read through the names. They made actually all the critical contributions in many aspects of the project, and including also theorists, also my experimental collaborators. And I would like to really highlight the 3 students, Eric, Jiaqi, and Jerome Park. They did the most work I talked to you today. And Jiaqi is going to MIT, Eric is going to France, but Jerome is looking for postdoc. So all I'm gonna say is he's the god of the lab. So yeah, he's the god. Here I highlight all the papers relevant to the talk I give to you today. Thank you.
I'm progressing.
Yeah, thank you. Do you think in these platforms there could be superconductivity like in microscopy selenide?
Yeah, so we've been looking for that. We see signatures, but we never seen RxS go to zeros. So I would say we haven't seen it yet. One possibility is that the system where you see I saw many ferromagnetic states. It's possible the spin interaction too strong.
Is there more magnetism in this platform than in tungsten diselenide?
There's also moiré magnetism, but that much smaller twist angle. Once you go large twist angle, the moiré magnetism just disappears.
Here it's more robust until upper.
Yeah. So I think that might be the reason. Yeah.
So in both the leaf data and squid data, it seems there's always a dip below, up, below what
Yeah.
what's that?
That's 4-9 state. 4-9, yeah. It's a state actually. But in MIM, in the squid and also in all the recent optical measurements, we'll see it. Yeah. So I think it's a robust state. The reason like I highlighted in the red font in my first lecture because we haven't seen the quantized anomalous salt yet. But other than that, I'll say probably it is another FCI state.
There's no more question, the last sense.